In the digital world, it's more convenient for computers to read binary formatted files compared to human readable text. Text requires slow and painful parsing. It also contains a lot of bloat compared to other formattings that are more compact. libc is the layer right above the kernel, and almost everything uses it. As a result, its APIs must be as fast and efficient as possible. This means that text formatted locals are not going to cut it. POSIX states that it's up to the implementation of how locals should be formatted and stored on a system. glibc reserves the /user/lib/local directory as the system-wide local archive. This is the default directory on GNU systems, which store all the system-wide locals. Any internationalized program running on the system can retrieve locals from the system's local archive. This is considered public, where contained locals are for public use. Some programs may have private application-specific locals not available for public use. These are not stored in the system-wide local archive. We'll expand on these situations later. The POSIX standardized local-def utility is used to compile or generate locals on a POSIX compliant system. As mentioned, POSIX deems the formatting of locals an implementation-specific detail. As a result, the formatting of compiled locals may differ between libc implementations of local-def, though our main focus are GNU systems, as mentioned earlier. glibc's implementation of the local-def utility gives us two methods of generating locals: through appending compiled data to the system-wide local archive file, or storing them as directories containing several binary files. Within the system-wide local archive exists a local archive file, which stores a number of system-wide locals in binary form. This is a memory-mapped binary file that can be read by any program to quickly and efficiently retrieve local information. Since the local-def utility is responsible for local generation or compilation on POSIX systems, glibc leaves the responsibility of archive file management to the local-def utility. GNU's implementation of local-def adds archive file management on top of its core POSIX functionalities. By default, local-def places all generated locals in the system-wide archive, whether it be the archive file or directory form. The noArchive argument pretty much says to add generated locals to the system archive in directory form, instead of appending to the archive file. So when you compile the foo local, for example, you will see a foo subdirectory in the system archive containing the local's information. The way these directory formatted locals work are pretty simple. The directory name is the local name, where its contents are the files describing the properties of the local. Each aspect or category, such as LC time, LC monetary, upon many others, have associated binary files to store their characteristics, essentially storing them as independent files instead of dumping everything into the system archive file. We can also generate locals outside the system-wide archive entirely, though this isn't local-def's default behavior. Passing a path instead of a name generates the local directory anywhere we want on the system. These are commonly known as private locals, since they exist outside the system-wide local archive that all programs access for local information on the system. This is useful for programs or users wanting to use custom locals instead of relying on system-wide ones. Since programs by default refer to the system-wide archive to look for locals, how can we instruct them to look elsewhere for private locals instead? It's not exactly a matter of telling applications themselves to look in different spots for locals. Rather, it's glibc APIs that fetch local information, which by default refer to the system-wide archive. So it's more so a matter of telling these glibc-provided functions to look elsewhere. We will expand on this subject soon. The localpath environmental variable alters the behavior of where these glibc APIs search for local data. This variable announces a directory that should be searched first, falling back to the default system archive if nothing is found. The core POSIX definition of the local-def utility is to be a compiler or generator of locals. GNU's spin of local-def adds additional features such as printing system archive information. This ability is limited in scope to printing information on the archive file, not the entire archive itself. POSIX gave us another utility whose sole purpose is to print out information of the entire archive, not just the archive file. Of course, GNU adds their spice of additional arguments and features to the spin of its local utility, though it doesn't change the bottom line. Looking at the POSIX standard, and even the slightly more complex GNU man page for it, the local-def utility is very simple, with only a few real important parameters. As a generalization, the local utility operates in two modes, first being to print out information about the local environment it executes in, and second being to print out information regarding the system-wide local archive. Let's discuss the first mode. Running the local utility naked has it print out information on the local environment, printing all the local categories and helper variables, such as lcall and lang. What's so useful about running the local utility in this mode is that it displays a glibc API view of the current environment. This may sound a bit confusing. What do we mean by this? Here, I wrote a quick custom shell script that prints all the local variables of the environment. As we see on my default shell environment on Ubuntu, only the lang variable is initialized and set, with all others not even being defined in the environment. The local utility makes use of implied values that are shown with quotations when printed to the screen. These are values that glibc APIs would assign to uninitialized variables when called. In this example, only the lang variable is defined, with all others being undefined. Lang has special semantical meaning to glibc, in that glibc assigns the value of lang to any uninitialized local category variable, such as lc numeric or lc messages. Thus, the local utility's use of implied values make it a potentially useful debugging utility to see how glibc API calls interpret the current local environment. The second mode, so to speak, is the archive mode, used by passing the "-a" argument. This displays all public locals found within the system's local archive. You may ask how this is different than using the localdef utility with the list archive argument discussed earlier. The localdef utility only deals with the management of the system's local archive file, not the local archive as a whole. Remember that the local archive file is only a subset of the system-wide archive on GNU systems. The local utility with the "-a" argument, however, dumps the contents of the local archive file as well as printing any additional directory formatted locals existing within the archive. This is extremely useful for users needing to check what locals are available on given systems. This utility becomes even more useful when used in combination with the "-v" argument. This prints out the local's metadata, including whether the local exists as a directory or part of the archive file, language, territory, character set, upon many other attributes. Note, however, that the local utility is limited in scope to only the system's local archive. The local utility will not pick up any private locals outside the local archive, even with the locpath environmental variable set. As mentioned, the GNU user space environment reserves the user share local as a place to store compiled, ready-to-use system locals. glibc also reserves the directory user share i18n as a place to store resources for localdef utility compilations. Here, instead of storing compiled locals, it's a place to store local definition files. Local definition files are text-based, human-readable files that describe the properties of locals and serve as input for localdef utility compilations. The i18n directory contains a bit more than just local definition files, as we will discuss later. Local definitions are more specifically stored in a subdirectory named local. There are two main schools of thought between Linux distributions regarding locals. First being that a system should come with very little available locals, but provide administrators the resources to compile their own as they become needed. The second school of thought being that a system should come with a fuckton of precompiled locals already, giving the administrator no resources to compile their own stuff. For example, Debian-style systems generally adopt the former philosophy, while Red Hat-style systems adopt the latter. Why give administrators resources to compile their own locals when the system already comes with all the locals they need, plus some? Running the local utility with the "-a" argument on Fedora shows that the system-wide local archive comes with virtually every language and region in existence, though its i18n directory is completely empty. You see just the opposite in Ubuntu, where the i18n directory is full of resource files to compile locals, though not many are compiled already. Note that this doesn't necessarily block administrators from compiling locals on Red Hat-style systems, as they could still download definition files from the internet to compile. One interesting variable between the schools of thought are the local archive file sizes, where the archive file on my Ubuntu system is around 5 megabytes, while the other Fedora machine's archive file consumes around 200 megabytes. Remember that archive files are memory mapped. As we know, a local is simply a preset of localization settings, where categories are subdivisions of these settings. Just as GNU adds GNU-specific categories on top of POSIX ones, GNU-specific settings are also sprinkled on top of POSIX settings. Local definition files have sections dedicated to each category of settings, each including a header, body, and trailer. Each section could be defined by scratch within the file itself, or it may instead reference another file section. glibc actually encourages the use of referencing to avoid redundant definitions. It's common to see the copy directive in definition files which provide this referencing feature. Interestingly enough, definition files exist which don't actually define locals themselves, or in other words, can't explicitly be used in compilations. These are considered helper definition files, and that their sole purpose of existing is to be referenced by other definition files. These helpers make files that actually define locals smaller, more readable, less redundant, and easier to deal with in general. As the goal of the gallery walk is to give you an idea of what each category does, I will not specify whether a particular category or localization setting is glibc or POSIX defined, as it doesn't really matter in this regard. C-type defines the properties of characters, categorizing them for different uses. Remember that in the eyes of the computer, characters are merely just code point values. They can't understand that the 6 character represents a number and the H character represents a letter. All the computer sees are 0x36 and 0x48 values. You can get away with hard-coding these properties if strictly working in a specific language, though for internationalized applications, these properties are instead defined in locals for better modularity. The C-type local category defines much more than code points corresponding to letters and numbers. Upper and lowercase fields specify which characters have what associated capitalizations. Alpha, short for alphabet, is a list of all code points included in the particular alphabet. This is required since some languages have characters or letters that are neither considered uppercase or lowercase, such as Mandarin, for example. Digit defines which code points are numeric. This is really a formality, since numeric characters are pretty universal. Punctuation would be a list of punctuation code points. Print is a fairly important field, as it draws a line into the sand as to which code points are able to print to the screen without screwing the terminal up, as some characters are non-graphical and have special semantical meaning to displays. LC collate defines collation, or how strings should be compared and stored. This can affect the behavior of regular expression engines, globbing, and internationalized utilities that implement sorting in some fashion. LC collate exists as many regions around the world have different conventions for text comparison and ordering. This is due to the fact that there are varying alphabets, alphabetical orders, capitalization or lack thereof, and other aspects to describe prior and LCC type. LC Cooley defines the sorting priority of letters, numbers, symbols, and capitalization. The LS core utility, for example, makes heavy use of LC Cooley to order printed listings. The sort man page even warns you about the effect of locals on sorting behavior. These rules may also be used for string comparisons within internationalized software. LC Messages defines the format of acknowledgement prompts. This category is heavily utilized before significant alterations to a system or environment, one example of which being package manager utilities. In other words, the LC Messages category is only really used for the "Are you sure you want to do this?" prompts. It defines the yes and no strings to print, which could be localized to various languages and scripts. As you may know from experience when dealing with acknowledgement prompts, you may enter acknowledgements in a variety of ways, such as typing yes using whichever capitalization order you want, or by simply typing single letters, such as Y for yes and N for no. As this could be a headache for defining a wide array of acceptable input, especially across locals of varying language and scripts, LC Messages makes use of regular expression definitions to implement this feature. LC numeric defines the formatting of numbers displayed on the screen, as many regions from around the world have differing conventions. For example, the radix, or decimal point, may be written with a comma, period, semicolon, or even a dash, depending on where the application is localized to. The same can be said about the thousandths place symbol. All the other categories should be pretty self-explanatory. If you're curious or wish to look at specific local fields offered by our system, take a look at the 5th and 7th man pages of the local utility. These also describe the specific libc APIs affected by each of the local categories. Local definition files really just describe characters themselves, not actually defining how those characters should be represented or encoded in memory. A perfect example would be the yes string and no string localization settings found within the LC messages category, more specifically, defining the particular code points that acknowledgement strings contain, not their encoded values. Definition files refer to characters through the use of abstract symbolic names and code points. Char map files are used to derive character encoding values from these abstract names and code points, making text ready for any real-world use. The use of char maps provide a level of modularity for local compilations. The idea is that local definition files could be compiled to use different encoding schemes by simply swapping interchangeable char map files. As charmap files are considered resources for compiling locals, they are present within the user share i18n directory reserved by glibc for storing local compilation resources, more specifically the charmaps subdirectory. As we have extensively discussed in the character set video, character names and code points are different layers of abstraction. Character sets map symbolic names to code points, with encoding schemes mapping code points to encoded values used in memory. Charmap files bundle the two of these aspects into one, mapping everything to each other. As a charmap file can map both code points and symbolic names to encoded values, both can be used to index the charmap file to retrieve encoded values. Despite the core motivation being modularity, you cannot freely mix and match local definition files with charmap files in any combination you want. This is primarily due to two reasons. The first issue being that all characters referenced by a given definition file may not be present within all the charmap files, thus interoperability would be problematic. And second, a character may have differing code points or symbolic names between charmap files. This would make character referencing problematic for charmap interoperability. The first remedy for these complications being that charmap files allow multiple symbolic names to be assigned to the same character. This makes charmap files more portable for use between a larger number of definition files. This is simply because a larger number of definition files may refer to the same character, but with different symbolic names. As both a character's symbolic name and code point may be common between charmap and definition files, sometimes only one of these attributes are similar. In these cases, the option of indexing charmap files with a choice of symbolic names or code points would be a second remedy. Although these band-aids exist to mitigate complications when mixing and matching char map and definition files, they cannot inherently eliminate them. Sadly, due to these mentioned complications, not all combinations of char map and local definition files are compatible. It's common to find char maps that are only really meant to be compiled with a select few or a single local definition file. These would be char map files of the various language-specific code pages mentioned in the earlier character set video. If char map files do come with your distribution, almost all of them will be these historic code pages. Although modern systems don't use these really at all, they're available for the sake of compatibility. Besides the discussed TriMap interoperability complications, there comes the pain of actually viewing the output of internationalized applications, whether that be a terminal or reading files via text editors. Available locals may have been compiled with differing TriMap files, which may have adopted differing character encoding schemes. As a result, bouncing between public locals may have strings display using different character encodings. Thus, one local's date and time strings may display perfectly fine, while another's may display as complete gibberish. To display them correctly, the user must manually configure their textual viewing application, whether it be a terminal or a text editor viewing redirected output. Not only is it a pain to constantly configure settings when hopping between locals, but the user is expected to know the particular encoding in use. Almost always, the user will have no idea, forcing them to use the local-av command mentioned earlier to figure it out. This is an extra step that makes the user experience that much worse. The Unicode character set defines symbolic names and code points for virtually every character in existence, thus being compatible with all local definition files. As we know, charmap files must define encoded values too, not just symbolic names and code points, which the Unicode standard defines. The digital world deemed UTF-8 as the de facto Unicode encoding scheme, with modern operating systems and internet almost strictly using UTF-8. Nowadays, since UTF-8 is almost always used in conjunction with Unicode, it's typically implied that Unicode and UTF-8 are unionized in a way. Thus, the terms UTF-8 and Unicode have become more or less synonymous, even though that's technically incorrect. This is analogous to people saying that they use Linux versus GNU/Linux, where just saying Linux is just easier to say. As a result, the name of the Unicode charmap file on GNU systems is literally named UTF-8. On modern Linux distributions, all public system locals are pretty much guaranteed to be compiled using this UTF-8 charmap file. Since all these locals were compiled using the same charmap, they all share the same character set and encoding. This fixes our problem of painfully and constantly configuring terminal display settings, due to UTF-8 Unicode being universal in a way. Switching gears back to distribution specific details, there are two main schools of thought regarding what locals should be present on systems. Unanimously, both aisles have all publicly available ready to use locals compiled with UTF-8. The include everything philosophy that Red Hat style distributions adopt has all publicly available locals compiled with UTF-8, though also provides the original versions of these locals that use their original language specific charmap files. The philosophy of include everything essentially mandates that all available system locals have a new age UTF-8 version and a original legacy version for the sake of compatibility. On the other side of the aisle is the slim everything down philosophy. For these distributions, not many locals come pre-compiled as it is. Having unnecessary legacy versions of locals for the rare case that something may need it is considered sacrilegious. Although distributions such as Ubuntu do provide facilities to compile locals with these legacy encodings. It's customary that compiled locals take the name of their corresponding definition file. This is true for legacy locals compiled with their original char maps. The same applies to locals compiled with the new age UTF-8 char map, though the string .utf8 is appended to the end of the local's name, as to differentiate them from their legacy counterparts. Besides, you wouldn't want to break things due to a name clash between archived locals on the system. The typical naming conventions for locals are name, territory, modifier, and encoding scheme. We have already discussed in part 1 why we require both language and region identifiers. These identifiers are two-letter ISO 639-1 language codes and ISO 3166 territory codes. At times, you may see a local with an @ symbol in the name. These are essentially identical copies of their naked counterparts, though change one or two things. They are useful for when a territory is going through a transitional period. For example, early 2000s banking systems required the use of two German locals, since Germany was transitioning from marks to euros over a 3-year period. To differentiate the original mark based local from the euro based local, the euro modifier was added. It's good to use the modifier when slightly modifying and recompiling an existing local definition file, though anything over a slight variation should get an entirely new name. As locals themselves don't really deal with an application's textual translations, Almost all internationalized programs in general use the getText API, as covered extensively in the last video. As getText requires more than just a front-end API, but an entire environment provided by libc, the directory user share local is reserved as glibc's getText message database. Messages and message databases were described in the last video. Internationalized applications have numerous message catalog files for textual localization, one for each of the application's supported languages. More specifically, one for each of the application supported locals, as differing regions that share a common language may have slightly different spellings. American English versus UK English, for example. Thus, message catalog files are more so tailored to locals rather than languages themselves. Typically, applications dump all their catalog files into the system-wide GNU message database, though some applications may opt to use their own private one instead. Programs have subdirectories in the /user/share as a place to store program-specific resources and configuration files. Programs such as the Vim text editor implement their own private message database at user/share/vim, for example. The motivation of private message databases are reduced potential conflicts and easier catalog file management. In practice, however, barely any programs make use of private message databases, dumping everything into GNU's system-wide message database instead. The only program I typically see making use of private message databases are Vim. Almost all internationalized programs running on the system dump their catalog files into the system-wide glibc database. This includes, but not limited to, GNOME applications, core utilities, the LibreOffice suite, browsers, systemd and daemons, GTK applications, package managers, and pretty much everything else running on the system that's internationalized. The structure of getText message databases are pretty bare bones. As individual catalog files are tailored to specific locals, databases organize them by local. Each supported local has a corresponding subdirectory in the database. These contain local-specific catalog files. For example, if I wanted to see all the American English catalog files within a database, I would simply refer to the associated US English directory. Regardless of whether a program's getText API is looking at a private or public message database, how does it know which individual catalog file to retrieve translations from? Simplistically, programs utilizing the getText API refer to the LC messages variable of its environment. In other words, the following variables in priority order. With these environmental variables, internationalized programs utilizing the getText API will be able to retrieve the translations of the correct language. This is a high-level overview. Let's take a slightly deeper look into getText's operation. A getText message database is structured and interpreted by getText as such. Dir name is simply the directory of the specific database in use. The default value of dir name is system-specific, being libc's provided message database. Local is used as an index into the message database, determining what language of which regional dialect should messages be retrieved from, as mentioned earlier. GNU documentation essentially states that the LC category section of the database structure should always be set to LC messages. I understand that getText primarily relies on the LC messages variable to determine target language, though if every category of every message database out there should be set to LC messages, what's the point of even having it in the first place? There's probably some historical reason or some other aspect I'm not seeing. Personally, I think it's unnecessary. A message domain refers to all the catalog files that are associated with a given program or package within a database. The nano domain corresponds to all the catalog files pertaining to the nano text editor. The core utility domain is used for all binaries of the core utilities package. A French user running systemd utilities requires messages fetched from the systemd domain of the French local, for example. The following code snippet is common between GNU core utilities, though many core utilities don't require textual translation, so they don't include it. libc utilities even have their own libc domains. libc APIs whose functionality are affected by locals, such as getText, don't actually read local environmental variables themselves. Instead, libc actually has a data structure that tells APIs such as getText which locals to use. POSIX defines the setLocal library call, which is used to modify this data structure. An interesting property of this call is that a null string passed to the local argument forces it to read the local environmental variables. This functionality is used by almost every internationalized program to adapt their behavior to the program's local environment. At times, all of a program's required translated messages are not found within one particular domain of catalog files, but instead spread across multiple. Suppose that we have an application that allows users to install plugins for extra functionality, such as CAD software or downloadable computer game mods. There will be a domain pertaining to the core vanilla application, though any additional plugins installed by the user may require a plugin-specific domain, assuming it's internationalized. To allow an application such as CAD software to bounce between domains when retrieving translated messages, GNU's text domain library call instructs APIs such as getText which domain to use. There comes another issue. It's quite possible that various domains used by an application are spread amongst different databases as a whole. An application's core domain may reside in libc's database, while a plugin's domain may live elsewhere. The POSIX bind text domain library call instructs APIs such as getText where certain domains live. By default, it's always assumed that domains live at the libc database, unless otherwise specified by the bind text domain POSIX library call. Many distributions actually implement their own distro-specific message database rather than relying on the libc provided one. Debian-style distributions such as Ubuntu commonly do this, while Red Hat styles generally stick to the good old libc database. These distributions try to move as many domains, or catalog files, out of the libc database as possible without breaking things. Though this is easier said than done, since internationalized functionality on my Ubuntu machine is currently broken because of this. Even domains of seemingly important OS related resources such as core utilities and libc utilities are housed within the distro implemented database as well, surprisingly enough. Though core operating system utilities are as much user space programs as Call of Duty is, for example, so I guess it's understandable. Ubuntu's distro specific database actually sits right next to the libc provided one in user/share, though it's named local langpack instead of just local, as the libc provided one is. Ubuntu has Langpack packages that can be installed to provide additional internationalization and localization support without touching the critical/core glibc database. I guess the rationale behind this was the ability for distributions to freely manage and configure databases without the fear of breaking something in the core libc database. Distros managing their own databases typically include GUI menus for user-friendly language management and configuration, worry-free. On Ubuntu, you may notice that there are still some files that didn't migrate and are still present within the glibc database. I'm assuming that these must have been considered too essential to be anywhere else on my Ubuntu system by maintainers. These domains contain translations for ISO standard language, country, script, and currency names. For example, a Russian Cyrillic local defines the ruble written in Cyrillic as the monetary unit, though it doesn't describe how monetary units of other countries are written in Cyrillic Russian. The ISO 4217 domain serves this purpose, specifying how another country's monetary units are written in Cyrillic Russian. The same concept can be applied to all these other ISO domains for language, country, and script names. Red Hat style distributions such as Fedora don't implement these types of databases, instead just chucking everything into the glibc provided one instead. Personally, I feel like this is a better approach, as simple is usually better. At the end of the day, however, a key takeaway from this section should be an awareness that some distributions implement their own message databases while others do not.